Good morning, everyone. Welcome to the Friday, July 8th lecture of ECE 2002. I don't really have too many administrative things to say. Just right now, homework 4 due on Monday. Hopefully we all make good progress on that. I would like to keep that deadline, but I might make it an adjustment if it proves to be too onerous. Because right now, the teaching staff and myself included are kind of behind on grading. So hopefully we get a little bit more caught up. All right. Let's go ahead and share my screen. And we'll jump right into new content today after we talked about, the different ways to do partial fraction expansion and take an inverse Laplace transform. Let's go ahead and jump right into impedance and admittance. So the idea is we'll generalize resistance into impedance and conductance into admittance. So remember, conductance was just 1 over resistance. We represented it with a G. And we'll represent admittance with a Y and impedance with a Z. So we're going to use a whole bunch of, capital letters now. So the idea is we're turning our linear differential equations into linear equations of S. So we're going to do some complex numbered algebra instead of ODEs. And this way we don't even have to take the ODE first. We could just build it into our circuit representation instead and, compactly represent our ODE that way. So for a resistor, by Ohm's law, VR as a function of time is equal to R times IR of t. Laplace transform both sides. R is just a constant, and IRT will just become capital IR of S. So we just get VR of S equals R times IR of S. So V is equal to R times I. Hey, still Ohm's law. Definitely looks like it. A conductor, so just the other way around. So IR of t equals G times VR of t. So IR of S is equal to G times VR of S. So if you want to think in terms of conductance of a resistor instead of the resistance of a resistor, you can do that as well. So now we're going to do something a little bit different. So we'll have an inductor. So we'll say VL of t is equal to L times DIL dt, the constitutive equation of the inductor. It's what defines the action of an inductor. So, and similarly, we'll have IC of t for the capacitor equals C times dVc dt, which is, the constitutive equation of capacitor. It defines what the capacitor does. So for the inductor, we'll get VL of S is equal to L times, in brackets, S times IL of S minus IL of 0 minus, where that is the Laplace transform of a derivative by definition. But if we're dealing with a circuit at rest, so this is a special case, a circuit at rest, we'll get VL of S is equal to SL times IL of S, where we'll say SL is the impedance of the inductor. And similarly for a capacitor, we'll get, IC of S is equal to C times bracket SVC of S minus VC of 0 minus, close bracket. Or IC of S is equal to S times C times VC of S when at rest in that special case, where we have the admittance of the capacitor Y being S times C. So, we can generalize impedance admittance for all elements, even the ones we didn't do directly because they're inverses of each other, remembering, Z is equal to 1 over Y. So we always get V of S is equal to Z of S times I of S, where for an inductor, Z of R is just R. Z for Z sub L is just S times L. And Z sub C is just 1 over SC. So this is the common way of dealing with it. We typically like thinking of resistances more than conductances for some odd reason, even though they're perfectly duals of each other. So the alternate way is to think in terms of admittances, Y of S. So Y sub R of S is just G, a constant. Y sub L is just 1 over SL. And Y sub C is SC. So now we can always write, our circuit using these generalized notions of resistance and conductance. And then all our resistive circuit techniques that we learned, so dividers, source transformations, Thevenin and Norton, maximum power transfer, can be used with RLC circuits. This is real similar to what you did with phasors, except, instead of using j omega, we're using S, because S is equal to sigma plus j omega. So we're including a real part in our S variable. So all of our resistive circuit techniques are good. Hopefully this is the part of ECE 20001 that everyone feels most comfortable with, so we can do examples without a hitch. So before we get into the examples, I wanted to first talk about some terminology, because we added a whole bunch of terminology, and Oliver Heaviside was the person who came up with this, namesake of the Heaviside cover-up method. He also is the namesake of the Heaviside step function, the continuous time step function. So some additional terminology. So to the complex components of impedance. So we talk about, Z. So in rectangular form, rectangular form of a complex number, the real part of Z is called R, which is resistance. That makes sense because, we saw the real number resistance show up. And the imaginary part of impedance is called X, or reactance. That's a new term. So we can write, Z is equal to R plus JX. And in polar form, we talk about the, magnitude, or the modulus of Z, which is the impedance magnitude. Doesn't really have a special name, thank goodness. It's just the impedance magnitude, which is the ratio of voltage to current in magnitude. And then we have the angle of Z, or the argument of Z, which is the impedance phase, the angle by which the current is behind the voltage. So it's like the amount of lag in the circuit. So we can do similar terminology to the complex components of admittance, by duality, all things we expect are here. So the real part of, Y, when looking at the rectangular representation, is called G, conductance, as we would expect. And the imaginary part of Y is called B, capital B, for susceptance. It's very easy to get confused with all these terms that end with A and CE. Definitely take your time to memorize these. These are things that get talked about with some regularity. If we look at the polar form of Y, so we'll get that the modulus of Y is called admittance magnitude, and that's the ratio of current to voltage in magnitude. And then the argument of Y is called admittance phase, and that is the angle by which voltage is behind current, or it's the amount of phase lead in a device or circuit. Any questions about these? This is just a little bit of memorization we have to deal with, as well as knowing the impedance of inductor, impedance of a capacitor, admittance of a inductor, admittance of a capacitor. Seeing no questions, let's go ahead and do an example. So let's do an example with impedance. So this is a circuit that starts at rest, so we can use our special forms of impedance. So here we have our time domain circuit. So we'll say V U of t, which is a step function voltage input, feeds into a resistor with resistance R and a capacitor, capacitance C. And, we want to find Vc of t, the voltage across the capacitor. So the first step we're going to do is take the Laplace transform of the source and turn all of our, R's and L's and C's into impedances. So in impedance land, And complex frequency land, S domain, we'll have V over S as our source. And then R just becomes R, stays the same. The voltage across the capacitor is now capital V sub C of S. And the impedance of the capacitor is 1 over SC, as we have discussed. So now we have a source with 2 impedances. Wait a minute. 2 impedances. Impedances act like resistance. We can just use a voltage divider equation. We're very familiar with, if we have 2 resistances, how to find the voltage across the lower resistor, given that they're in this configuration. Now we can use, voltage divider with impedances. So VC of S is equal to Vn of S times ZC over Z sub R plus Z sub C. So we plug in what the impedances actually are. So we'll get VC of S is 1 over SC over R plus 1 over SE, fraction into fraction, compound fraction. And then we have V over S. So we can simplify. So we'll multiply the denominator through by the S. We'll multiply top and bottom by C, capacitance, and we'll get VC of S is equal to V over S times quantity, R times C times S plus 1, close quantity. Now, again, we don't like having any coefficient other than 1 in front of our pole factors. So we can divide everything through by RC, so we can reintroduce some of these fractions and make it a compound fraction again. So we'll get VC of S is equal to V over RC all over S times quantity S plus 1 over RC, close quantity. So again, this is just dividing top and bottom by RC. Well, now we have, a polynomial on top and a polynomial on bottom. Polynomial on top is just a constant polynomial. The polynomial on bottom is a quadratic polynomial. We can do partial fraction expansion to figure out how these will go back into the time domain. So we'll do partial fraction expansion with A1 over S plus A2 over S plus 1 over RC. So doing the cover-up method, so I'm using my thumb right here. So we'll cover the S in our original VC of S is equal to V over RC over S times quantity S plus 1 over RC, close quantity. We'll cover the S in the denominator and plug in the value that makes that term I covered 0. So what makes that 0? 0 itself. So I'll get V over RC over 0 plus 1 over RC. Well, that's just V over RC over 1 over RC. The 1 over RC's cancel. And I get that A1 is equal to just V. Now I'm going to take my thumb, cover the S plus 1 over RC term, figure out its coefficient. So what makes S plus 1 over RC equal to 0? Well, that's S equals negative 1 over RC. So plug in S equals negative 1 over RC into what is remaining. And we get V over RC over negative 1 over RC. The RC's 1 over RC's cancel, and we're left with A2 equals negative V. So we perform the inverse Laplace transform, and we get VC of t equals V times quantity 1 minus e to the negative t over RC, U of t. What questions do we have? Yep. AJ, you're absolutely right. Remember, the impedance admittance work just like the phasor one, except remember we have S equals, sigma plus j omega. So now we're considering the transient response in addition to just the sinusoidal steady state response that you would get with j omega. Because if you were to do the exact same work, using j omega, you wouldn't get this, e to the negative t over RC component. You would just get that VU of t type of component if you were trying to solve this with phasors. It'd be a little bit weird, but you could do it. Specific reason to use impedance instead of admittance, or is it possible to use either method? It's possible to use either method, but we use resistors when we're talking about voltage division. So we want to use impedances because they're the counterparts of, resistors. Put another way, when we're dealing with series components, we like dealing with resistances because resistances in series add. So we like to deal with impedances when we have components in series. And then when we have components in parallel, we like to deal with admittances because conductances in parallel add. Impedances for series components. Is easier. Out of curiosity, inverse Laplace transform B for f of s equals s. Just s in the numerator. I think it is. Oh, okay. We can solve this by duality. So if we take the inverse Laplace transform of t times u of t, we get 1 over s squared. So if we just have f of s equals s, by duality, we would get 1 over t squared. Or something like that. The other way to think of it is, oh God, it's not very well defined. I'll just tell you that. The other way to think of it is, multiplication by s is the same thing as taking a derivative. So it's the derivative of the thing that has Laplace transform of 1. So it would be the derivative of the delta function, which would be, some monstrosity that I don't like talking about. Don't expect it. See, S does not like to live in the numerator by itself. That's why we specifically said we're going to deal with functions, rational functions where, m is less than m. The degree of our numerator is less than or equal to our denominator. That's just how we tend to have things work out. Yeah. Forget what I said about 1 over t squared. It's the derivative of the delta function. And if you really want to know what the derivative of the delta function looks like, take the derivative of a Gaussian function, take the limit of that as of that derivative Gaussian function as the standard deviation goes to 0, and you get something that looks like, as you're going, let's see, left to right, you get something that looks like a positive spike, and then there's a negative spike, and then they suddenly start to collide until eventually it's 2 spikes on top of each other, one going up and one going down. See, I tell you, this is why you don't want to think about such things, Granov. It's the path to madness. What function has values of positive infinity and negative infinity overlapping each other? Only at time equals 0. Okay, let's move on to our admittance example. So find IL of t, the current in this inductor, with value L, given that this circuit starts at rest. So we'll use an exponential input, I1 e to the bt, u of t. And then we've got a capacitor as well with capacitance C. So we'll take the Laplace transform of our source and write admittances. So we're going to move to the complex frequency land, and this time I'll write it using admittances. We normally don't write things this way on the circuit diagram, but I told the viewer that I was doing this, and I did so as the first step of the next slide. So I'm writing admittances instead of impedances. So we'll have I1 over S minus B, which is the Laplace transform of our source, 1 over SL, the admittance of the inductor, and S times C, the admittance of the capacitor. So let's see how this LC tank circuit solves. So we can use current division. Remember, for a current divider, we'll get IL of S is equal to YL over YL plus YC. It divides based off of its own conductance over the sum of the conductances. So thus it works the same with admittances. So simplify the expression for IL of S. IL of S is equal to 1 over SL over SC plus 1 over SL times our IN of S, which is I1 over S minus B. Let's see, we'll multiply through by SL. We'll get I1 over quantity LCS squared plus 1 times quantity S minus B. We'll divide through by LC so that we get a unit coefficient in front of the first S squared. So we'll get IL of S is equal to I1 over LC all over quantity S squared plus 1 over LC, close quantity times quantity S minus B, close quantity. So by partial fraction expansion, we'll get IL of S equals A1 over S minus B, and then plus A2 times S plus A3 over S squared plus 1 over LC. Remember, when we have this quadratic term in the denominator, where we're missing the linear term, we need both a linear term and a constant term, this sort of affine form in the numerator. Yeah. This class is like, 3/8 a math class, so might as well teach you some math terminology. So we'll solve with S equals B. So we'll get A1 equals I1 over LCB squared plus 1. That's what you get when you solve this out. When you equate, what's on the left here with what's on the right. And we'll solve with 0 to figure out the A3 term. So you work that out. The partial fraction expansion is a little bit messy. I've kind of skipped to the results a little bit. But you'll get something that looks like this. Or by getting a common denominator, you'll get A3 is equal to negative I1B over LCB squared plus 1. So it's the negative of our A1 term times a B. And then our S equals 1 term, you work this out. It is really messy. And it took me a few tries to get the right answer here. But you eventually get A2 is equal to negative A1. So A2 is equal to I1 over LCB squared plus 1. So we have to massage the sine-like term. So we'll multiply by omega naught over omega naught, where omega naught is 1 over square root LC, as we would expect. And we'll get the following after our inverse Laplace transform. So we'll get I1 over LCB squared. That's equivalent to saying I1 over B over omega naught quantity squared plus 1. Times the quantity e to the positive VT minus cosine of omega naught t minus B over omega naught sine of omega naught t, close quantity times U of t. And if we were to go, pause for a moment, open lecture set 2, jump to the LC circuit. This looks very similar. In fact, it's exactly the same as what we got back on slide 35 of lecture set 2. So I'll make note of that. Slide 35 of lecture set 2. Proving that, yeah, these methods are exactly the same, except instead of using 11 steps as we did for this, we did it in 5 steps. So that's kind of neat. What questions do we have? Thanks for joining us, all the newcomers. So I'll just type it out. A linear equation would be like a times x. Affine equation would be a times x plus b. Hopefully that makes some sense to you. Sorry about that sound. I know it sounds weird. I forgot to mute myself. Okay. Hearing no more questions, we'll move on to the next topic. If my computer will register what I'm doing. Nope, it won't. Open lecture set 4. Okay. So now slide 55. I'm going to remind you that the Laplace transform of a derivative of a function is equal to s times the Laplace transform of that function minus the initial condition at time equals 0 minus. Region conversions, real part of s greater than 0. So if a circuit is not at rest, then we must account for all the energy stored in the reactive elements prior to the analysis interval. So, that basically means we have to account for, the electric energy stored in the capacitor, the magnetic energy stored in the inductor. That's the 1/2, CV squared or the 1/2 Li squared type of energy. So the ODE method required us to store the initial conditions as an initial value problem and then solve after we got the particular solution and, the homogeneous solution with unknown coefficients. Then we used the initial values to solve it. So we were, mentally storing the information aside until we needed it. Laplace transform method actually incorporates the sources for the initial condition alongside impedances and admittances. So, this is going to be kind of convenient. We're going to get everything stored in the circuit rather than have to, write out, hey, this is what's going on at some later step. We're good at circuits, Sometimes our memory isn't the best. So let's do a mathematical example. So we're going to solve RC dVc dt plus VC with Vn equal to Vu of t and Vc of 0 minus not equal to 0 by Laplace transform. So we'll take the Laplace transform of the source in ODE. Vn of s is equal to V over s equals RC times quantity s times Vc of s minus little Vc of 0 minus closed quantity plus Vc of s. So we'll solve for Vc of s. So let's see, we'll regroup and we'll get, Vc of s, Rc of times s plus 1, closed quantity, minus Rc of Vc of 0 minus equals V over s. Or, let's see, moving things around. So we'll resolve the subtraction by moving it to the other side. Then we'll divide through by Rc of s minus 1. So we'll get V over s plus Rc Vc is 0 minus all over Rc of s plus 1. Let's see. We'll factor 1 over s out of top and bottom, and then divide through by Rc so that we get a unit coefficient in front of this term. So we get Vc is 0 minus equals Vc 0 minus s plus V over RC all over S times quantity S plus 1 over RC closed quantity. So again, like I said, we have to be good at our algebra in order to do these types of problems. So definitely, practice as much as you can. Work things out the long way. And please, if you're the person who makes mistakes and know it, do things in more steps than I show it. It's okay. Please, show more steps if that's what you need to do things right. Like, I'm doing things in fewer steps so that it fits nicely on a slide and I could present in a sensible amount of time. But, if you want to do things, in a more granular fashion, go right ahead. I'm fairly good at algebra and I'm not intimidated by it, as you can tell by how many symbolic expressions I'm willing to manipulate. So I do things my own way. So we'll do partial fraction expansion. So we'll have a linear polynomial over a quadratic polynomial. We'll rewrite it as, A1 over S plus A2 over S plus 1 over RC. You can do some cover-up method. So you plug in S equals 0, cover up the S in the denominator. 0, you get V over RC over 1 over RC. So you'll just get A1 equals V. Cover-up method, cover up the S plus 1 over RC in the denominator. Set S equal to negative 1 over RC. You'll get, V minus VC, VC is 0 minus. Actually, I did that wrong. Cover it up. We're putting the negative 1 over RC. So we'll get negative V, and then negative and negative is plus VC of 0 minus. Yeah, and that's what I have in line 3. So we'll perform the inverse Laplace transform. We'll get quantity V plus, in parentheses, the initial condition minus capital V, close parentheses, e to the negative t over RC, close brackets, U of t, which matches what we would expect for, a sort of, charged series RC circuit, or series RC circuit with a charged capacitor. This is what we've dealt with before. So obviously, we still have this ODE, and it would be nicer if we could reduce it to even fewer steps by putting our initial conditions into the circuit, itself. Right now, we did a fairly good job. It was our initial condition was embedded into the partial fraction expansion resolution in the Laplace transform method, rather than being a separate part of the initial value problem from the ODE. So we're going to put it in the circuit and make things even easier on ourselves. So this is the best way to do it if you were to rank the ways of doing it. So first we'll derive what we need to do. So capacitor initial conditions. So we'll take the Laplace transform of the capacitor constitutive equation. So IC of t is equal to C dVc dt. Well, we get IC is equal to S times C VC of S minus C times VC of 0 minus. That's just multiplying C through by, SC minus VC is 0 minus. Well, we know what SC is. We already defined it as the admittance of the capacitor. So we get IC of S is equal to this current, YC of S times VC of S, minus a different current, C times VC is 0 minus. So, this is saying, okay, this is like two currents. So the frequency domain current through the capacitor equals the admittance times the frequency domain voltage minus a constant current that depends on the initial condition right here. So if we were to interpret this in the time domain, that last term at least in the time domain, what we're getting is an impulse of area C times VC of 0, which if you check out the units, capacitance times voltage is charge by definition. So what we're doing is, applying a impulse of current that injects the right amount of charge for the initial conditions at the instant analysis begins. So it's basically saying, hey, this is a one-sided Laplace transform. We're going to, at the start of analysis, inject that much current and then analyze the circuit. And, that puts the charge on the capacitor needed to start the problem off correctly. Well, there's another way we can deal with this. So if we manipulate this equation, okay, or I guess this equation, move things around, we will get this. VC of S, the frequency domain voltage, equals the impedance, 1 over SC, times the frequency domain current, plus a frequency dependent voltage that depends on the initial condition, this last term right here. So the time domain interpretation of this last term is that it is a step, VC is 0 minus, that turns on the right amount of voltage across the capacitor at the instant the analysis begins. So like, okay, that makes sense. We know we're one-sided Laplace transform, everything's off, and then suddenly we need to turn a step to put the right amount of voltage across the capacitor at the instant analysis begins. That will match our initial conditions. So in circuit form, we have this. So IC of S is equal to YC times VC of S minus this current. So watch the polarity. This current opposes the overall current of the capacitor. And notice this overall current goes through both components. So this current being, C VC is 0 minus in S domain land. And then we have VC of S being defined across both components. Make sure of that. ZC, this generic impedance right here. And then represented by a box. Same with the generic admittance, I guess. And then we have this voltage working in concert with it. So VC is 0 minus over S, a nice step domain voltage, or a step function voltage. What questions do we have? These are the most efficient ways to represent initial conditions using Laplace transform methods. Brain bendy. I mean, you want your brain to be flexible, but like. Any questions? All right. You know how electrical engineering courses work? Duality time. Time to talk about the exact same thing we just talked about, but with an inductor, hoping that the repetition helps cement the ideas in your brain. That's a good teaching technique to do, is just say the exact same things with different words. Hopefully it helps make the idea stick. So we'll take the Laplace transform of the inductor constitutive equation. VL of t is equal to LTIL dt. We'll get VL is equal to, well, L times SIL of S minus L times IL of 0 minus. So we interpret this as voltage equation as the frequency domain voltage equals impedance times frequency domain current minus a constant voltage that depends on the initial condition. So voltage equals voltage minus voltage. So this voltage is L times IL of 0 minus the initial condition. So the interpretation of this one is that there's an impulse of area L times IL of 0 minus that injects flux linkage. And if you haven't taken an electromagnetics course, you may be wondering what is flux linkage. Basically, it's the amount of magnetic flux lines going through something. So in this case, if your inductor is a coil, it's the amount of magnetic flux lines going through your coil. So that much magnetic flux is needed in order to start the inductor at the right level of energization. So we can manipulate this equation, move things around, divide by L, simplify by dividing by S, and we'll get this right up here. So we interpret the current equation as there being two current components. So frequency domain current is the admittance, 1 over SL, times VL of S, the frequency domain voltage, plus the initial condition divided by S, which is a frequency dependent current. Did I say current earlier? Yeah, I should have been saying current earlier. So the time domain interpretation is of a step function, IL, a 0 minus U of t, that turns on the right amount of current through the inductor at the instant analysis begins. So once I Laplace transform, everything starts off, and then suddenly we, force the right amount of current through our inductive admittance so that, our analysis is correct. In circuit form, it's going to look like this. So VL is defined across both these components in this view of the world. IL of S is going to flow through ZL, and then it works such that IL is 0 minus works in opposition to the overall voltage. Or we have the current being defined through both components, and we have our generic admittance symbol Y sub L, and then we have this current that works in concert, IL is 0 minus divided by S. And you're like, how am I possibly going to remember this? Well, remember, capacitors are voltage things. Capacitors like being in series with things. Well, I guess, voltages, we like to deal with voltages in series because they just kind of stack and add by KVL. So, remember, we'll have step function initial conditions that work together. Similarly, inductors are current devices. They like being in parallel because when currents in parallel add. So we'll just say the current into the overall inductor is just its admittance plus, this step current that works in concert with it. And then the other transformation is just the dual. The dual form. So yeah, this is basically what I'm saying here. The voltage step of the capacitor series model may be treated as an independent voltage source. So yeah, this looks like an independent voltage source. Then, the inductor parallel model, this looks like an independent current source. In the parallel model, we can just solve these circuits with superposition. So yeah, we can just, solve for any applied sources while turning off this source, solve the state of the circuit, then turn off the applied source, solve with the initial condition source, and solve the circuit, add them together, and that's the overall response, because these are linear circuits. Now, the alternate forms where we're dealing with, the capacitor parallel model or the inductor series model, those are just the Thevenin and Norton equivalents of each other to what I just said. But the key idea here is we'll be able to solve circuits with superposition, which is great. Superposition is a wonderful technique that we used to solve, resistor circuits before. I got an oh no. Why is there an oh no? Let me resolve your confusion as best I can. Exam is 2 weeks from today. Yeah, because this is week 4. The next exam is week 6. I think an example will make things a little bit easier. I hope. So here is an initial condition in Laplace example. So find IL of t, the current through this inductor in this parallel RL circuit, given that In of t is the step function I times u of t, and IL of 0 minus is not equal to 0. Darn. So we can't just solve this at rest. We need to apply what we just learned. Funny that we should have to do that immediately after I discuss that. So on top, we have the time domain circuit. We're going to take the Laplace transform of everything and get the frequency domain circuit. So we'll get I over S for our step function current source, applied current source. I'll write things with admittances. So R becomes 1 over R in admittance land. This current becomes IL of S into both of these components, which is VL of S, the voltage across the inductor, with admittance 1 over SL. And we have a current source by our current source model. It works, in the same direction as the overall inductor current that we got from our original circuit definition. And it is a step function with IL of 0 minus over S. We can solve this circuit. I'll read from slide 60 while leaving this up with superposition. So first of all, we need to find the current that goes through the inductive admittance. So basically the current that just goes through, the curly Y sub L. So from I in, we turn it off the other source. So this just becomes an open circuit on the right. So I sub YL1 is going to be I over S times 1 over SL divided by 1 over R plus 1 over SL. That's how it works. And then we're going to turn off the applied current source and do the current division with our initial condition current source. So we'll get that the current through the curly Y sub L is, again, voltage by the voltage division, 1 over SL over all over 1 over R plus 1 over SL times IL of over S, IL of 0 minus over S, I should say, with a negative sign. Because remember, we define the current going down through this device. This current will force the current to go up through the inductor instead of going down through it. So we need a negative sign. It opposes our, passive sign convention. So altogether, if we add up both components, let's see. Well, we got this 1 over S bit, so we get I minus IL 0 minus all over S times, we multiply both sides by RSL. And we get, or I guess we just multiply through by, just SL. We get 1 over S all over SL over R plus 1. Are you with me so far? This is superposition. But again, you have to be good at math in your algebraic manipulations, or specifically your algebraic manipulations. Yeah, that's supposed to be subtraction because we have to add these two current components together. There's a negative sign there, so we have to have a minus sign. Unless you mean the next line down, where everything is okay. So remember, we did not find the total inductor current. We only found the current through the curly inductive admittance. We need the total current. So I sub L of S, the total current through the inductor, which is what we want, is that bit through the admittance plus the original IL0 minus of S. So by KCL, IL of S is equal to the inductive admittance current plus the original current. So that's equal to, by simplification, R over L times quantity I minus IL0 minus all over S times quantity S plus R over L, which was our bit right here, plus IL0 minus over S. Now is the time we need to do partial fraction expansion. So we have these two terms. This is a 1 over S bit. This is a 1 over S bit plus a 1 over S plus R over L bit. So we can just combine this into, say, VC of S is equal to A1 over S plus A2 over S plus R over L. If you do partial fraction expansion for the Y sub L bit and the IL over S bit, you'll end up having to do the same work twice. And no one likes doing partial fraction expansion more than they have to. So wait until after you get your desired quantity, in this case IL of S, before you do partial fraction expansion. You want to do partial fraction expansion to get the original thing. Also, this is totally a typo right here. That should be, instead of VC of S, that should be I sub L of S. Just realized that. Now, you'd have to massage this a little bit to get it into a form you like. But if you were to do partial fraction expansion on this, maybe you would combine some like terms, or get a common denominator to get like terms. You would get that A1 is equal to I, and A2 is equal to IL0 minus I. So by inverse Laplace transform from our table, IL of t is equal to, this becomes I times U of t, and this becomes IL0 minus capital I times e to the negative R over L times t U of t. And that is our answer. And this matches exactly the answer we would expect for a parallel RL circuit. I mean, yeah, but you need the ODE. So you have to remember how to write this ODE, which is, adds a step or two. So yeah, you can do that, AJ. If the problem says, though, use a Laplace transform method to solve this problem, you shouldn't be finding the ODE, though. So you have to watch what the instructions allow you to do. And Aubrey said, never mind. Any more questions? If not, I'll keep lecturing. So the third topic of today will be transfer functions. So remember, the output of a linear time invariant or LTI system at rest is y of t is equal to x of t convolved with h of t. That nasty convolution. So we can get the impulse response h of t by taking the derivative of the complete step response. Remember, the derivative of a convolution is the same thing as the convolution with one of the signals differentiated. So yeah, that allows us to get the impulse response by taking the derivative of the complete step response. Remember, it's to a unit step or to a unit impulse function. By the convolution property, we get a multiplicative form for the output of the LTI system. So in the frequency domain, y of s is equal to x of s times h of s. The other way of saying this is h of s is equal to the ratio of y of s to x of s, which is the Laplace transform of our output to the Laplace transform of our input. So the transfer function, as we'll call it, capital H of s, is going to be written using impedance and admittance forms with our circuit techniques. So this allows us to define basically behavior of our circuit regardless of the input being used. So as a note, knowledge of the transfer function, capital H of s, allows for the output of any system at rest to be computed for any given input, as we would expect. The transfer function is going to abstract away the entire topology of the underlying circuit. And if you ever wondered what I meant by topology, that's like the specific choice of components and their interconnections that make up the circuit. So it's like, it's basically the layout of the circuit, or the complete schematic, you know, the choice of components, their values, and how they connect to each other. All of that doesn't matter. Once we have the transfer function, it just becomes math. Transfer function itself is the Laplace transform of the at-rest response of the circuit to the unit impulse. Yep, you know, these are Laplace transforms of each other, so that makes sense. And having either h of t or capital H of s is good enough to find the other. Now, we're running short on time. I will take any remaining questions. Otherwise, I wish you a good weekend. You know, stay safe, have some fun, but also do your homework. Goodbye, everyone. You're welcome, everyone. Have a nice weekend.